California has been too quiet for too long. And in seismology, silence isn't peace, it's accumulation. Right now, as you're listening to this, the San Andreas fault system sits in what geophysicists call a seismic gap, wedged between recent major releases in Alaska and Mexico like a locked link in a breaking chain. But here's what should concern you. In the first week of January 2026, 3 completely unrelated planetary systems lit up within days of each other. A solar storm compressed Earth's magnetosphere. The Schumann Resonance spiked into unusual territory, and a deep-sea creature from the abyss washed ashore in Monterey Bay. The exact same sequence appeared before Kamchatka's mega-quake last year. The big one might not be coming. It might already be here. Subscribe and follow along, because the signals we're seeing right now might not be warnings. They might be the beginning of something Earth has been arranging for longer than we realized. Something unusual happened in the first week of this year. You probably didn't notice it. Most people didn't. But scattered across 3 continents, instruments started registering anomalies that individually would raise an eyebrow. Together, they form a pattern that makes seismologists lean forward in their chairs and speak a little more quietly. This isn't about one freak occurrence that broke the internet for 48 hours and then vanished. This is about multiple systems, completely unrelated systems, lighting up within days of each other. The magnetosphere compressed. The Schumann Resonance spiked into unusual territory. A creature from the abyss washed ashore in California. And if you know anything about planetary history, you know that clustered anomalies matter more than isolated ones. Much more. Earth doesn't usually spike like this. Its systems operate on different timescales, different rhythms. Geomagnetic disturbances follow solar cycles. Deep sea biology responds to ocean chemistry and pressure. Seismic activity builds over decades, sometimes centuries. When these separate clocks suddenly synchronize, even for a moment, it's worth paying attention. Because historically, that's when the planet does something we weren't expecting. The solar storm hit on January 2nd, 2026. It wasn't the strongest we've ever recorded, not even close, but timing matters more than raw strength. This storm arrived when Earth's magnetosphere was already under stress, already compressed from previous solar wind pressure. Imagine a balloon that's been squeezed for days, and then someone squeezes harder. The balloon doesn't pop, but its shape warps. It pushes inward in some places, creating pressure differentials that ripple through the entire system. That's what happened to Earth's magnetic shield. The magnetosphere, which normally extends about 60,000 kilometers into space on the sun-facing side, got pushed inward. Not catastrophically, not apocalyptically, just enough to change the distribution of electromagnetic energy flowing through and around our planet. And here's the thing about energy. It doesn't disappear. It goes somewhere. 2 days later, monitoring stations around the world detected something strange in the Schumann Resonance. If you're not familiar, the Schumann Resonance is essentially Earth's electromagnetic heartbeat, a set of frequencies created by lightning discharges resonating in the cavity between the planet's surface and the ionosphere. It usually hums along at about 7.83 Hz, with some natural variation. But on January 4th, stations recorded sustained energy in the higher frequency bands, 14 Hz, 20 Hz, even higher, persisting for hours. This wasn't a single spike. This was sustained activity in ranges that typically stay quiet. And while no mainstream scientific body will tell you that Schumann resonance anomalies predict earthquakes, there's a small but growing body of observational data showing these electromagnetic shifts appearing in the days following major seismic events. Not before, after. As if the planet's electrical environment is responding to stress we can't yet measure directly. The scientific status here is important. Schumann resonance is not an earthquake predictor. It's not even officially linked to earthquakes. But pattern recognition doesn't require official blessing. Observers noticed it after Sumatra in 2004, after Tohoku in 2011, after the Kamchatka mega-quake last year. The electromagnetic signature shows up in the data, whether or not we understand why. Then came the fish. On January 5th, researchers at Monterey Bay Aquarium Research Institute reported a rare deep-sea species washing ashore near Moss Landing. The exact species identification is still debated. Some say ribbonfish, others argue it's a juvenile oarfish, but the debate misses the larger point. Deep water species rarely surface unless something below changes. Pressure shifts, temperature anomalies, chemical gradients in the water column. These creatures live in a stable, high-pressure environment. When they abandon it and swim upward into hostile conditions, something pushed them. Monterey Bay isn't just any coastline. It sits adjacent to one of the most geologically active zones in North America. The San Andreas Fault System runs offshore here, and the Monterey Submarine Canyon, one of the deepest underwater canyons on the continent, creates a unique environment where deep ocean processes interact directly with shallow continental shelf dynamics. If there's anywhere on the California coast where subsurface stress might first express itself through biological signals, it's here. This exact sequence happened before. In early 2025, weeks before the Kamchatka megaquake, observers reported similar clustering, a moderate solar storm, electromagnetic anomalies, and unusual deep-sea fish sightings along the Coral Trench. The similarities are striking enough that some researchers are now calling this a pre-seismic signature, not predictive, but suggestive. A pattern without a proven mechanism. Which brings us to the uncomfortable hypothesis gaining traction among a small group of geophysicists. What if California isn't building stress in the traditional sense? What if it's receiving it? Standard earthquake science treats faults as isolated systems. Stress accumulates locally. Plates lock. Energy builds. Eventually, the fault ruptures and releases that energy. It's a savings account model. You deposit stress over time, then withdraw it all at once. But Earth isn't a collection of isolated systems. It's a coupled, rotating sphere where energy can redistribute in ways we're only beginning to understand. If solar energy can compress the magnetosphere, and if that compression alters electromagnetic environments near geologically active zones, and if those zones are already mechanically stressed from plate motion, then what we're seeing might not be a countdown to a single event. It might be a leak. Energy finding weak points. Not triggering earthquakes, but modulating when and where accumulated stress finally lets go. The mainstream won't say this, not officially, because the mechanism isn't proven. The data is correlational, not causal. But ask yourself, when Earth's protective systems don't fail evenly, where do they leak first? Where does energy arrive before anyone expected it? If this is a leak, the next question isn't where stress builds, it's where it arrives. California's problem isn't that it's been shaking, it's that it hasn't. Look at a map of significant earthquakes around the Pacific Rim over the last 18 months. Alaska, magnitude 7.2, October 2024. Mexico, magnitude 7.5, March 2025. Peru, magnitude 7.0, September 2025. These aren't random dots. They form a geographic sequence along the Pacific margin, a chain of releases moving through the ring of fire like a slow-motion wave. Now look at California. Silence. Not complete silence. Small quakes happen constantly, but nothing above magnitude 6 since Ridgecrest in 2019. For a fault system as active as the San Andreas, that's not peace. That's accumulation. Seismologists have a term for this: seismic gap. It's not a countdown, not a prophecy. It's a pressure imbalance. When surrounding areas release energy and one section doesn't, that section becomes mechanically isolated. The stress that would normally distribute across multiple fault segments concentrates in the quiet zone. and Northern California right now sits in that zone. The concept is straightforward. Imagine a chain where some links break and release tension. The remaining intact links now carry more load than they were designed for. They don't break because they're weak. They break because everything around them already broke. This is why seismologists track where earthquakes didn't happen as carefully as where they did. The gaps tell you where the stress is hiding. The Pacific Plate isn't polite. It doesn't wait for California to feel ready. It's moving northwest at about 2 inches per year, grinding against the North American plate, whether the San Andreas accommodates that motion or not. When the fault is locked, the stress doesn't vanish. It translates into elastic deformation of the crust. The rock bends, strains, stores energy like a compressed spring. Eventually, something has to give. Current models identify Northern California, specifically the section between Parkfield and the Mendocino Triple Junction, as having elevated probability for a significant event. Not the big one, necessarily. Not magnitude 8, but magnitude 6.5 to 7, which, for most of the public obsessed with disaster movies about Los Angeles crumbling into the Pacific, sounds almost disappointing. It shouldn't. A magnitude 6.5 in the right place, at the right depth, with the right rupture characteristics, can be far more destructive than a larger quake in a remote area. San Francisco sits on filled land, artificial soil, sediments that amplify seismic waves. The same shaking that might feel moderate in Parkfield could resonate through the Bay Area with devastating efficiency. Buildings constructed to modern codes will likely survive. Older structures, bridges with outdated designs, underground utilities. Those are the vulnerabilities. And resonance matters more than raw magnitude. A 6.5 that shakes for 20 seconds at a frequency that matches building response periods causes more damage than a 7.0 that shakes for 10 seconds at a different frequency. There's a dangerous quirk in how automated seismic hazard models work. When an area stays quiet for a long time, the models often interpret that quietness as safety. The reasoning goes, if a fault hasn't ruptured recently, maybe it's less active than we thought. Maybe the recurrence interval is longer. Maybe the probability should be downgraded. It's the seismic equivalent of assuming that because your smoke detector hasn't gone off in 5 years, your house must be fireproof. This is aftershock logic applied to pre-rupture environments. After a major quake, seismologists expect aftershocks, so they monitor closely. Before a major quake, especially in a region that's been quiet, monitoring continues, but urgency decreases. The problem is that pre-rupture stress indicators, when we can even measure them, often look like nothing unusual until they look like everything at once. The public fixates on magnitude. The media fixates on magnitude. But geophysicists know that location, depth, and rupture propagation direction matter just as much. A magnitude 6.5 centered 20 kilometers beneath downtown San Francisco, rupturing upward through the crust, would be catastrophic. The same magnitude centered 80 kilometers offshore, rupturing horizontally, might cause minor damage and a lot of nervous headlines. This isn't about the biggest earthquake. This is about the most disruptive placement. And right now, Northern California sits between recent energy releases like a quiet link in a chain that's been breaking around it. The stress corridor along the Pacific margin is active. California is mechanically isolated within that corridor. The gap isn't a guarantee, but it's an exposure, an elevated probability that feels less like random chance and more like a target being painted. The mainstream position is clear. Seismic gaps do not predict timing. They indicate where future ruptures are more likely, but not when. Could be tomorrow. Could be decades from now. This uncertainty is supposed to be reassuring. It's not. Because uncertainty cuts both ways. If we can't predict timing, we also can't rule out that the timing is now. What we're seeing doesn't feel like buildup. It feels like positioning, like the planet is arranging pieces on a board, and California is the piece that hasn't moved yet. When everything around you shifts and you don't, you're not stable. You're next. If stress is moving through Earth's systems, the next question is how it travels through a spinning planet. On January 8th, 2026, a magnitude 5.3 earthquake struck near the Prince Edward Islands in the southern Indian Ocean. Unremarkable magnitude, remote location. Most people never heard about it, but some geophysicists noticed immediately, not because of what happened, but because of where it happened. Draw a straight line through the center of Earth from Monterey Bay, California. Where does it emerge on the opposite side? Near the Prince Edward Islands. Almost exactly. These are called antipodal points, opposite locations on a sphere, geometrically mirror images through the planet's center. And sometimes, for reasons science still can't fully explain, when one side of Earth ruptures, the opposite side responds. Not always, not predictably, but often enough that it shows up in the data as more than coincidence. The phenomenon isn't new. Researchers have documented potential antipodal correlations after major earthquakes for decades. The 2004 Sumatra quake had antipodal seismic activity reported near the Galapagos. The 2010 Chile quake corresponded with unusual tremors in China, nearly antipodal. The 2011 Tohoku event preceded swarms near the Azores. Each case is circumstantial. Each case lacks a proven mechanism, but the pattern persists. Classical plate tectonics struggles with this. Plates move. Faults rupture. Energy releases locally. The idea that a rupture on one side of the planet could influence the opposite side, thousands of kilometers away, through solid rock and liquid iron, doesn't fit neatly into the models we've been using for 50 years. Yet, the correlations keep appearing. Enter the torque hypothesis. It's speculative, controversial, and increasingly difficult to ignore. Earth isn't just a stack of rigid plates grinding past each other. It's a rotating system, a sphere spinning at roughly 1,000 miles per hour at the equator, slightly slower at higher latitudes, with a molten outer core, a solid inner core, and a semi-plastic mantle in between. When stress builds asymmetrically, when one part of the crust locks while others move, it creates rotational imbalance. Think of a bicycle wheel with a broken spoke. The wheel still spins, but it wobbles. The missing spoke doesn't just affect the rim where it broke, it affects the entire wheel's balance. Now scale that up to planetary size. If a major fault system locks and accumulates stress, it changes the mass distribution of the crust ever so slightly. Not enough to slow Earth's rotation, not even close, but potentially enough to alter how stress distributes through the mantle over time. This is where angular momentum becomes relevant. Earth doesn't just shift plates horizontally, it spins them through three-dimensional space. Stress applied in one location doesn't necessarily stay in that location. It can transfer vertically through the mantle, especially if the mantle is already convecting, already in motion. And if stress is being transmitted vertically through Earth's interior, then antipodal points aren't random. They're geometrically inevitable. The math here gets complex quickly, but the intuition is simple. Imagine squeezing a water balloon on one side. The pressure doesn't just push outward at the squeeze point, it redistributes through the fluid, creating bulges on the opposite side. Earth's mantle isn't water, but it behaves plastically over long timescales. It flows. And if it flows, stress can couple between distant points in ways purely surface-based models wouldn't predict. The Kamchatka mega-quake in 2025 reignited interest in these global coupling theories. A magnitude 8.3 rupture that shifted the seafloor by meters, followed within weeks by unusual seismic swarms on the opposite side of the planet in the South Atlantic. Coincidence? Pattern recognition error? Or evidence of a planetary scale stress transfer mechanism we haven't fully characterized? Science operates on proof, not patterns. The torque hypothesis lacks the direct evidence needed for mainstream acceptance. We can't drill through Earth's mantle to watch stress propagate in real time. We can't rewind the planet and run controlled experiments. What we have are observations. Earthquakes that correlate antipodally more often than random chance would predict, and no widely accepted mechanism to explain why. This is where scientific humility matters. We know Earth behaves as an integrated system: atmosphere, hydrosphere, geosphere, all coupled through energy exchange. But our models still treat the geosphere as mechanically segmented, as if faults operate independently. What if they don't? What if the planet communicates internally in ways we're only beginning to detect? The Prince Edward Islands quake was small. Monterey Bay is quiet. There's no proven link. But the geometry is exact. The timing is suspicious. And if Earth is behaving less like stacked plates and more like a stressed rotating shell, then maybe we've been looking for mechanisms in the wrong place. Maybe the question isn't whether stress transfers through the planet. Maybe the question is who notices first. If the planet communicates internally, who else might be listening before we do? Animals don't predict earthquakes. Let's be clear about that from the start. There's no mystical connection, no cosmic intuition. Cats don't see the future. Dogs don't receive telepathic warnings from the Earth. But they do sense things humans can't. And dismissing every historical account of unusual animal behavior before seismic events as folklore might be throwing out valuable observational data along with the superstition. The historical record is extensive and cross-cultural. Ancient Greek accounts describe snakes fleeing cities days before earthquakes. Chinese records from the 14th century document unusual behavior in horses and livestock before major quakes. Japanese fishermen reported bizarre catches, deep-sea species appearing in shallow nets before the Tohoku disaster. Italian farmers insisted their animals acted strangely before L'Aquila in 2009. Every culture with earthquake history has these stories. Modern science has largely ignored them, and for good reason. Anecdotes aren't data. You can't build a predictive model on, "My dog seemed nervous." Pattern recognition in retrospect is notoriously unreliable. Humans are excellent at finding connections after the fact. But what if the problem isn't that the observations are wrong? What if the problem is that we've been dismissing them without investigating the mechanisms that might explain them? Animals experience the world differently than humans do. This isn't controversial. It's basic biology. Dogs hear frequencies we don't. Migratory birds sense magnetic fields. Sharks detect electrical gradients in water. Marine mammals navigate using pressure sensitivity that far exceeds anything we can consciously perceive. These aren't supernatural abilities. They're sensory adaptations to environmental variables that humans simply don't prioritize. Now apply that to tectonic stress. When rock deforms under extreme pressure, it doesn't just bend, it changes the local electromagnetic environment. Piezoelectric effects in quartz-rich rocks generate small electrical currents when compressed. Radon gas can seep from microfractures in stressed crust, altering atmospheric chemistry near fault zones. Pressure changes in deep aquifers can propagate through groundwater systems faster than seismic waves travel through rock. All of these are measurable, physical phenomena. Deep sea species are particularly sensitive to electromagnetic gradients because they navigate through an environment where light is absent and chemical cues disperse slowly. Electric fields, pressure waves, and magnetic variations become primary sensory inputs. An oarfish living at 600 meters doesn't need to predict an earthquake. It just needs to detect a change in its environment significant enough to trigger a flight response. If tectonic stress is altering electromagnetic conditions in the water column above a fault zone, the fish doesn't know why the environment feels wrong. It just knows to leave. This is why the species identification debate about the Monterey Bay sighting is somewhat beside the point. Whether it was a ribbonfish or an oarfish or some other deep-dwelling species matters less than the behavior. Something from a stable, high-pressure environment abandoned that environment and swam into conditions where it couldn't survive. That's not random. That's a response to stimulus. The repetition problem is where this gets interesting. If these were isolated incidents, one fish before one quake, we'd call it coincidence and move on. But the pattern keeps reappearing. Japan has documented over 20 instances of oarfish strandings or sightings in shallow water within weeks of significant seismic events. Chile has similar records. New Zealand. California. The data isn't perfect, but it's there. Science struggles with this because the mechanism isn't proven. We can theorize about piezoelectric effects and electromagnetic sensitivity, but we can't measure the exact electromagnetic environment a deep-sea fish experiences in real time before an earthquake. We can't run controlled experiments. We can't replicate the conditions. So the scientific method, which demands reproducibility, gets stuck. The observations are suggestive, but not conclusive. This is where folklore becomes relevant, not as mysticism, but as archived pattern recognition. Ancient observers didn't have seismographs. They didn't understand plate tectonics, but they watched the world carefully because their survival depended on it. When they noticed that certain animal behaviors preceded earthquakes often enough to remember and record, they weren't inventing superstition. They were documenting patterns without having models to explain them. Modern science often makes the mistake of assuming that because historical observers lacked our theoretical framework, their observations must be invalid. But observation predates theory. You don't need to understand electromagnetism to notice that migratory birds behave strangely before a storm. You don't need to understand piezoelectricity to notice that deep-sea fish sometimes appear before earthquakes. The challenge is extracting the signal from the noise. Most unusual animal behavior doesn't precede earthquakes. Most earthquakes don't have documented animal anomalies beforehand. The correlation is weak, inconsistent, and impossible to use for prediction. But weak doesn't mean absent. Inconsistent doesn't mean meaningless. It means we don't understand the variables yet. What if biological responses to pre-seismic stress aren't predictive signals, but reactive ones? What if animals aren't detecting the earthquake itself, but responding to environmental changes that humans can measure but don't consciously perceive? We have instruments that can detect electromagnetic shifts, radon emissions, pressure anomalies. We just don't correlate them with seismic risk because the mechanism linking them isn't established. The Monterey Bay fish appeared 5 days after the solar storm, 4 days after the Schumann Resonance anomaly. Correlation doesn't equal causation, but correlation at least suggests we should be looking for causation. If deep-sea species respond to electromagnetic environment changes, and if solar storms can alter those environments near geologically active zones, and if those zones are already mechanically stressed, then maybe what we're seeing isn't prediction. Maybe it's detection of a variable we haven't learned to monitor yet. If biology reacts to invisible shifts, what about the invisible systems protecting the planet? Solar storms do not cause earthquakes. This needs to be stated clearly and repeatedly because the correlation has been weaponized by sensationalism and pseudoscience for decades. The sun does not trigger seismic events. There is no direct causal link between solar flares and fault ruptures. The scientific consensus on this is solid, and it should be respected. But there's a subtler question that consensus doesn't address. Could solar energy influence when accumulated stress releases? The magnetosphere isn't a force field in the science fiction sense. It's not a solid barrier that deflects threats. It's a dynamic region where Earth's magnetic field interacts with the solar wind, a constant stream of charged particles flowing from the sun. Most of the time, this interaction is stable. The magnetosphere extends far into space on the day side, stretches into a long tail on the night side, and funnels solar particles toward the poles, where they create auroras. It's beautiful, elegant, and mostly predictable, except when it's not. Solar storms, coronal mass ejections, high-speed solar wind streams compress the magnetosphere like a squeezed balloon. The compression doesn't damage anything directly, but it redistributes electromagnetic energy through Earth's upper atmosphere and ionosphere. This redistribution is measurable. It affects radio communications. It disrupts GPS signals. It induces currents in long-distance power lines. The energy is real, the effects are documented, and the mechanisms are well understood. What's less understood is how this electromagnetic energy couples with Earth's interior systems. The ionosphere and the magnetosphere are electrically connected to the surface through Earth's global electrical circuit. The Schumann Resonance, those electromagnetic frequencies resonating between the surface and ionosphere, is part of this circuit. When the magnetosphere compresses, the entire circuit experiences altered energy distribution. Now, here's the speculative part. If tectonic stress generates piezoelectric currents in compressed rock, and if the magnetosphere compression alters the electromagnetic environment near fault zones, could there be coupling between these systems? Could external electromagnetic stress modulate the timing of seismic stress release? This isn't saying solar storms cause earthquakes. It's asking whether they might affect the probabilities of when existing stress lets go. Think of it as a straw breaking a camel's back scenario. The camel was already overloaded. The straw didn't create the problem, but it was the final variable that triggered collapse. Could solar electromagnetic energy act as that final variable for faults already near failure threshold? The problem is, this variable isn't in earthquake models. Not because it's taboo or because scientists are ignoring it out of stubbornness, but because it's nearly impossible to test. You can't run controlled experiments on tectonic plates. You can't isolate variables when studying planetary scale systems. And when you're dealing with phenomena that happen on timescales of decades or centuries, establishing causation through observation alone requires more data than we have. Interdisciplinary research struggles here because disciplines operate with different standards of evidence. Geophysicists want mechanical models, stress calculations, fault friction parameters, rupture propagation physics. Space physicists work with electromagnetic coupling, plasma dynamics, charged particle interactions. The two fields use different mathematical frameworks, different terminology, different journals. Bridging them requires researchers fluent in both, and those are rare. This is why the Schumann resonance anomalies get dismissed so easily. The measurements are real. Stations around the world recorded the elevated frequencies. But because there's no accepted mechanism linking electromagnetic activity to seismic activity, the measurements get filed away as interesting but irrelevant. Science rewards narrow expertise, not broad pattern recognition across disciplines. Yet the pattern persists. Solar storms correlate with elevated Schumann resonance activity. Schumann resonance anomalies appear in temporal proximity to large earthquakes. Deep-sea biological signals appear in the same windows. The correlations aren't perfect, but they're frequent enough that simply dismissing them as coincidence starts to feel like willful blindness. The magnetosphere's role here isn't as a trigger, it's as a modulator, a system that redistributes energy in ways that might interact with Earth's internal stress states. If electromagnetic coupling between the solar wind, ionosphere, and geologically active regions exists even weakly, then periods of heightened solar activity could shift the probabilities of seismic events without causing them directly. This isn't about prediction. Even if the coupling is real, even if solar storms do modulate seismic probability, the effect would be so small and the timing so uncertain that it wouldn't be useful for forecasting specific earthquakes. But it might help explain why clustered anomalies, solar, electromagnetic, biological, sometimes precede major seismic events. Not because one causes the other, but because they're all responding to or contributing to a planetary stress state that's approaching a critical threshold. Earth isn't a collection of independent systems. The atmosphere affects ocean circulation. Ocean circulation affects climate. Climate affects ice sheet stability. Ice sheet loading affects crustal stress. Everything couples with everything else through energy exchange. The magnetosphere is part of that coupling, and the solar wind drives the magnetosphere. Ignoring external energy inputs when studying internal stress systems might be a methodological convenience, but it's not physically realistic. The issue isn't lack of data, it's lack of integration. We measure solar storms. We measure magnetosphere compression. We measure Schumann resonance. We measure seismic activity. But we analyze them separately, in isolation, as if the connections didn't matter. Maybe they don't, but maybe we haven't looked carefully enough to find out. If Earth is entering a sensitive state, other sciences may already be seeing it. In late December 2025, a team of geophysicists published findings in Nature Geoscience about newly mapped complexity at the core mantle boundary beneath the Pacific Ocean. Using seismic tomography, essentially CT scans of Earth's interior using earthquake waves, they discovered regions where heat flow from the outer core into the mantle is far more uneven than previous models suggested. This matters because heat flow drives mantle convection, and mantle convection drives plate tectonics. If heat distribution is uneven, then convection patterns are uneven, which means the forces pushing and pulling tectonic plates aren't uniform. Some regions of the Pacific plate might be under more stress than others, not just because of plate boundary interactions, but because of what's happening 3,000 kilometers beneath the surface. Earth isn't thermally uniform. The core isn't a smooth, evenly heated engine. It's turbulent, chaotic, with temperature variations that create complex flow patterns in the liquid iron outer core. Those patterns generate Earth's magnetic field through dynamo action, but they also create pressure and temperature gradients that propagate upward into the mantle. The mantle responds by flowing, and that flow ultimately manifests as plate motion at the surface. What the recent research shows is that the core mantle boundary beneath the Pacific is particularly complex, regions of ultra-low velocity zones where seismic waves slow dramatically, suggesting partial melting or unusual composition. These zones might act as stress concentrators, channeling heat and pressure upward into overlying mantle, which then transmits stress to the crust above. California sits above one of these complex regions. The implications go deeper than simple stress transfer. These ultra-low velocity zones represent regions where the physics changes fundamentally. Material properties shift. Wave propagation behaves differently. Energy that would normally dissipate uniformly through the mantle instead concentrates, creating hotspots of thermal and mechanical stress thousands of kilometers below the surface. We've known these zones existed for years, but the new mapping reveals they're larger, more interconnected, and more dynamically active than previous models suggested. Think of it like plumbing in an old building. You assume water pressure is uniform throughout the system until you map the actual pipe network and discover bottlenecks, corrosion, and unexpected connections that create pressure variations from room to room. The Pacific mantle beneath California isn't uniform pipe. It's a complex network where some pathways channel more energy than others. And right now, one of those high-energy pathways sits directly beneath one of the most seismically vulnerable regions on the planet. Meanwhile, in an entirely different field, artificial intelligence systems trained on decades of seismic data have started identifying correlations that human analysts missed. Not because humans are incompetent, but because the correlations exist in high-dimensional parameter space, relationships between dozens of variables across time and geography that don't resolve into simple patterns a human can spot by eye. One AI system, trained on global earthquake catalogs, identified weak but statistically significant correlations between solar storm intensity and seismic event timing in specific tectonic environments. Not everywhere. Not all the time. But in geologically active regions with accumulated stress, the correlation was above random chance. The researchers who published this were careful to emphasize they hadn't proven causation, only correlation. But the correlation exists in the data. This is exactly the kind of finding that makes traditional scientists uncomfortable. It's not a mechanism. It's not a theory you can test in a laboratory. It's pattern recognition in massive datasets revealing relationships we don't yet understand. The AI doesn't know why solar storms correlate with earthquake timing in certain regions. It just knows they do, with statistical confidence that exceeds random noise. Human intuition would never spot this, because the relationship involves too many variables interacting across too many dimensions. We need machines to see what we can't. The skeptical response would be to dismiss this as data mining. Run enough statistical tests, and you'll find spurious correlations everywhere. And that's valid criticism. Except this particular correlation has been found independently by multiple AI systems trained on different data sets using different architectures. When separate approaches converge on the same pattern, it's harder to write off as algorithmic artifact. This is how modern science increasingly works. We're moving away from simple linear causation, A causes B, toward complex systems, thinking where multiple variables interact in nonlinear ways to produce emergent behavior. Earthquakes aren't caused by one thing. They're the result of mechanical stress, heat flow, fluid pressure, electromagnetic coupling, rotational dynamics, and probably variables we haven't identified yet, all interacting in a system that's perpetually near a critical threshold. The shift represents a fundamental change in epistemology, how we know what we know. Classical science demands isolating variables, controlling conditions, establishing clear causal chains. But Earth systems don't cooperate with laboratory conditions. You can't isolate a tectonic plate. You can't run controlled experiments on mantle convection. You can't rewind time and test whether solar storms actually influence seismicity. The system is too large, too complex, too interconnected to study using traditional reductionist methods. So we're learning to think in terms of probabilities rather than certainties, correlations rather than mechanisms, emergent behavior rather than direct causation. This doesn't mean abandoning rigor. It means expanding our toolkit to include statistical inference, machine learning, network analysis, and systems theory, alongside traditional hypothesis testing. Critical thresholds are where things get interesting. Near a critical point, systems become hypersensitive to small perturbations. A slight change in conditions can trigger massive reorganization. This is true in physics, ecology, climate science, and increasingly appears true in seismology. Earth's crust isn't gradually building to inevitable failure. It's hovering near criticality, where small inputs can have disproportionate effects. The concept applies beyond earthquakes. Climate systems near tipping points respond dramatically to small forcing. Ecosystems near collapse points lose resilience to minor disturbances. Financial markets near instability crash from triggers that wouldn't matter in stable conditions. The principle is universal. Complex systems near critical states behave differently than systems far from those states. Phase transitions in physics follow similar principles. Water at 99 degrees Celsius is still liquid. Water at 100 degrees becomes steam. That 1 degree of temperature change, a tiny input, produces a complete reorganization of molecular structure and system behavior. The system was already at the critical threshold. The small additional energy just pushed it over. If Earth's seismic systems are near criticality in certain regions, if California's faults are loaded close to failure threshold, then variables that would normally be irrelevant might suddenly matter. Solar electromagnetic coupling that typically has zero effect might tip the balance when stress is already at 99% of failure strength. It's not the primary cause, but it could be the final nudge. This is why noise increases before system shifts. Complex systems approaching critical transitions often show increased variability, more fluctuations, more anomalies, less stability in baseline measurements. In seismology, this might manifest as increased microseismicity, unusual electromagnetic readings, changes in groundwater levels, or, speculatively, biological responses to environmental shifts we can't yet quantify. The phenomenon is called critical slowing down in systems theory. As a system approaches a critical threshold, it takes longer to recover from perturbations. It becomes less stable, more responsive to small pushes. You see this in financial markets before crashes, increased volatility, larger price swings, faster correlation between supposedly independent stocks. You see it in ecosystems before collapse. Population fluctuations increase, recovery times lengthen, resilience decreases. And you might be seeing it in Earth's seismic systems, electromagnetic noise increasing, biological anomalies appearing, microseismicity fluctuating more wildly. Earth's background electromagnetic hum, the Schumann Resonance, geomagnetic variations, ionospheric currents, becomes noisier when the system is stressed. Not because the electromagnetic activity causes the stress, but because stressed systems interact differently with external forcing. A stable system absorbs perturbations smoothly. A stressed system amplifies them unpredictably. It's like the difference between a well-tuned guitar and one with loose strings. The well-tuned guitar produces clean notes, even if you pluck the strings hard. The loose-stringed guitar produces dissonant overtones, buzzing, unpredictable harmonics. The input, your finger plucking the string, is the same. The response changes because the system's internal state changed. The research from this month doesn't prove anything about California specifically, but it establishes context. Earth's internal heat distribution is more complex than we thought. AI is finding correlations in seismic data that suggest nonlinear interactions, and complex systems theory increasingly applies to planetary science. These aren't isolated developments. They're pieces of a larger shift in how we understand Earth as an integrated dynamic system, rather than a collection of independent processes. When multiple lines of evidence from different disciplines start converging, even if none of them alone is conclusive, it's worth paying attention. Not because it proves the hypothesis, but because convergence suggests the hypothesis might be asking the right questions. Earth isn't just accumulating stress in California. It's integrating energy from multiple sources, tectonic, electromagnetic, thermal, in a region that's already mechanically loaded. The convergence matters more than any single data point. If only the core mantle research existed, we'd file it away as interesting geology. If only the AI correlations existed, we'd suspect algorithmic artifacts. If only the biological anomalies existed, we'd dismiss them as coincidence. But when research from geophysics, computer science, space weather, and marine biology all start pointing toward increased complexity, increased coupling, and increased sensitivity in Earth systems, the convergence itself becomes evidence that something about our understanding needs updating. This isn't apocalyptic. It's systemic. The danger isn't that we don't know enough. It's that we've been asking the wrong questions. We've been trying to isolate causes when we should be studying interactions. We've been looking for linear relationships when the system behaves non-linearly. We've been treating Earth as machinery when maybe it's more like an organism, integrated, adaptive, responding to multiple inputs simultaneously in ways that aren't reducible to simple formulas. If the question itself is wrong, the answer will always surprise us. The obsession with prediction has made us stupid about preparation. Every time seismologists appear in the media, the question is the same. When will the big one hit? What's the date? Can you give us a timeline? And the scientists, constrained by honesty and uncertainty, respond that earthquakes can't be predicted, which is true, which is also useless, because the question itself is flawed. Earthquakes aren't discrete events that happen on a schedule. They're moments in ongoing sequences of stress accumulation, release, and redistribution that never stop. Earth's crust is always moving, always deforming, always approaching or retreating from failure thresholds in different locations. Asking, when will it happen, treats earthquakes like appointments on a calendar. They're not. They're phase transitions in a continuous process. The analogy that works better is weather versus climate. We can't predict exactly when it will rain 3 weeks from now, but we can say with confidence that Seattle will be wetter than Phoenix this year. We can identify conditions that favor storms without knowing the precise moment lightning will strike. Seismology has been trying to be meteorology, predicting specific events, when maybe it should be more like climatology, characterizing risk over time and space without claiming to know exactly when and where. This framing problem has real consequences. Communities prepare for the big one, the magnitude 8 or 9 disaster that will flatten cities and generate tsunamis, while remaining vulnerable to magnitude 6 or 7 events that would still collapse infrastructure, sever supply chains, and disrupt millions of lives. The obsession with worst-case scenarios creates a blindness to likely case scenarios. And magnitude 6.5 in Northern California is a likely case scenario, not a worst-case one. The psychological fixation on catastrophe is understandable. Hollywood trains us to think in terms of spectacle. News media amplifies extreme scenarios because they attract attention. But this fixation creates a weird paradox where people either prepare for total apocalypse or don't prepare at all. There's no middle ground. Either you're a prepper with a bunker and 5 years of food, or you're someone who figures there's no point worrying. Because if the big one hits, we're all doomed anyway. The reality is much more boring and much more actionable. Most earthquake damage comes from medium magnitude events in populated areas, not mega-quakes in remote locations. The 1989 Loma Prieta earthquake was magnitude 6.9. It killed 63 people, caused $6 billion in damage, and collapsed a section of the Bay Bridge. Not apocalyptic, just catastrophically disruptive to millions of lives. That's the scale of event California should be preparing for, because that's the scale of event that's actually likely. Preparedness fails when prediction dominates the conversation, because people wait for warnings that will never come. If scientists can't tell us when, the reasoning goes, then we can't know when to prepare. So why bother preparing at all? It's a psychological trap. The absence of specific prediction gets interpreted as absence of specific risk, when the reality is that the risk is constant and elevated. This is fundamentally a problem of human psychology meeting scientific uncertainty. We're pattern-seeking creatures who evolved to respond to immediate identifiable threats. A lion in the grass, a snake on the path, dangers you can see and react to. We're terrible at responding to probabilistic, long-term risks where the threat is always present but never immediate. Climate change has the same problem. Financial risk has the same problem. Pandemic preparedness has the same problem. We know these things are dangerous, but because the danger isn't happening right now, this specific moment, we defer action. Institutions are even worse. Building codes get updated after disasters, not before them. Infrastructure budgets prioritize visible problems, the bridge that collapsed last year, over invisible ones like the bridge that might collapse next year. Seismic retrofitting is expensive and politically unglamorous. It's easier to fund emergency response after an earthquake than resilience measures before one. Comfort with old models means waiting for failure rather than adapting to new understanding. There's a name for this in policy circles: the disaster response cycle. Catastrophe strikes. Public attention surges, money flows, reforms happen, then attention fades, budgets shrink, maintenance gets deferred, and gradually, over years or decades, the system becomes vulnerable again. We saw it after Hurricane Katrina, after the 2008 financial crisis, after every major earthquake. The cycle repeats because institutional memory is short and political incentives favor visible action over invisible prevention. What makes this particularly frustrating is that we know how to build earthquake-resistant structures. The engineering exists. Japan has demonstrated it repeatedly. Modern building codes, properly enforced, can prevent most earthquake deaths. But retrofitting existing structures is expensive, disruptive, and politically difficult. Homeowners don't want to pay for it. Landlords resist upgrades. Politicians don't want to mandate costly requirements that might slow development or anger voters. So we wait. We accept the risk. We hope it won't happen on our watch. There's a deeper issue here about how we conceptualize Earth itself. The standard plate tectonic model, brilliant and revolutionary when developed in the 1960s, treats the planet as passive machinery. Plates grind, stress accumulates, faults rupture. Everything is mechanical, deterministic, and, given enough data, theoretically predictable. But what if Earth isn't passive? What if it's a dynamic, coupled system where electromagnetic, rotational, thermal, and mechanical variables interact in ways that don't reduce to simple causality? Modern physics gave up on strict determinism decades ago. Quantum mechanics embraces probability. Chaos theory shows that deterministic systems can be fundamentally unpredictable. Complex systems, science studies emergence, how system-level behavior arises from component interactions in ways you can't predict by studying components in isolation. Yet, earthquake science still largely operates within a deterministic framework where, if only we had enough data, we could calculate exactly when faults would rupture. This isn't a criticism of seismologists. They're doing excellent work within their paradigm. It's a question about whether the paradigm itself is adequate for the system we're trying to understand. The mechanistic model works beautifully for understanding how faults move, how stress accumulates, how ruptures propagate. But it struggles with timing. It struggles with triggered events. It struggles with explaining why some fault segments rupture together and others don't. Maybe these aren't failures of the model to be fixed with more data. Maybe they're limitations inherent to modeling a complex adaptive system with deterministic equations. Maybe we can't predict earthquakes, not because we're not smart enough or don't have enough sensors, but because the system doesn't work that way. Maybe earthquake timing emerges from interactions between dozens of variables operating on different timescales, with coupling mechanisms we're only beginning to understand, in a system that's constantly near criticality, where tiny perturbations have large effects. If that's true, then prediction in the traditional sense, knowing exactly when and where, might be impossible in principle. And here's the thing, that's okay. We don't need prediction to take action. But preparation isn't impossible. Resilience isn't impossible. Understanding isn't impossible. We can build structures that survive magnitude 7. We can design infrastructure with redundancy. We can maintain emergency supplies. We can plan evacuation routes. We can educate communities about what to do when shaking starts. None of that requires prediction. It just requires accepting uncertainty and preparing for it. The Japanese approach is instructive here. Japan can't predict earthquakes any better than California can. But Japanese building codes are stricter. Earthquake drills are routine. Emergency supplies are standard in homes and offices. Cultural expectations around preparedness are higher. When magnitude 9 struck Tohoku in 2011, the earthquake itself killed relatively few people. Most deaths came from the tsunami, which is harder to engineer against. The buildings performed remarkably well. That's not because Japan can predict earthquakes. It's because Japan accepted they can't, and prepared accordingly. The signals we've been discussing, solar storms, electromagnetic anomalies, biological responses, aren't alarm clocks. They're not countdown timers. They're weak, cross-disciplinary indicators that something in Earth's state might be shifting. We don't know how to interpret them yet. We don't know if they're causally connected or just correlated, but dismissing them entirely because they don't fit established models is a failure of curiosity. Science progresses by noticing things that don't fit, then investigating why. The history of geology is full of observations that were dismissed as folklore or coincidence until someone figured out the mechanism. Continental drift was mocked for decades before plate tectonics explained it. Meteorite impacts were considered impossible until the evidence became overwhelming. Established models resist change because they're intellectually comfortable. But comfort isn't the same as correctness. Alfred Wegener proposed continental drift in 1912. The evidence was obvious. Coastlines that fit together, matching fossils on separate continents, geological continuity across oceans. But the mechanism wasn't clear, and without a mechanism, the scientific establishment rejected it. Wegener died in 1930. His theory still considered fringe nonsense. It took until the 1960s, with seafloor spreading data and paleomagnetic evidence, for plate tectonics to become accepted. 50 years of resistance to an idea that was fundamentally correct because the framework for understanding it didn't exist yet. We might be in a similar place with earthquake science. The observations are there: electromagnetic anomalies, biological responses, solar correlations, antipodal patterns. The framework for integrating them doesn't exist yet, so they get dismissed. But dismissal isn't the same as disproof. California's situation right now isn't about inevitability. It's about exposure. The stress is accumulated. The gap is identified. The surrounding areas have released energy. The solar electromagnetic biological clustering has occurred. None of this guarantees an earthquake tomorrow or next week or even this year. But it establishes elevated risk in a region where infrastructure and population density make that risk consequential. The worst response isn't panic. Panic is at least a response. The worst response is pretending nothing spoke because the language doesn't fit our models. Multiple systems are exhibiting anomalies within a compressed time frame near a known seismic gap. That's information. What we do with it depends on whether we're willing to ask different questions. Not when will it happen, but how resilient are we if it does? Not can we predict it, but can we survive it? Not what's the mechanism, but what's the pattern? Science seeks mechanisms, and it should. But while we're waiting for mechanistic proof, the patterns continue. The correlations persist. The clustering repeats. Earth operates on its own timescale, following rules we're still learning to read. We've mapped the faults, measured the plate velocities, calculated recurrence intervals. We've built sophisticated models and deployed sensor networks. We've learned an enormous amount about how the planet works. But we still approach it with a 20th century mindset: deterministic, reductionist, mechanistic, when maybe we need a 21st century perspective that embraces complexity, uncertainty, and integration across disciplines. The opening anomalies, the compressed magnetosphere, the Schumann spike, the deep-sea fish aren't proof of impending disaster. They're signals in a language we don't fully speak yet. Ignoring signals because we don't understand the grammar is a choice. Listening to them, investigating them, preparing for what they might indicate, that's also a choice. When systems whisper together, the worst response isn't panic. It's pretending nothing spoke.